Okay, welcome back. So, in the previous class, we have started with a discrete time signals. So, in that we have seen impulse sequence. Let's go with the next signal, which is nothing but discrete time unit step sequence. Unit step sequence. It is represented with a u of n. Its value may be 1, its value may be 0. So it is similar to that u of t only, but exactly some difference we are having. When n greater than or equal to 0, means at equal to 0 also we are having the value is 1. Okay, and for n less than 0, its value is 0. So that's what the u of n. So if I represent this graphically, at n is equal to 0, its value is 1. So everywhere 1, 1, 1. So this is the graphical representation. For every instant n is equal to 0, 1, 2 like that. So it is going to be 1. For less than 0, that is minus 1, minus 2 like that. For those values, its value is 0. Okay. Suppose if I want to represent this with a sequence of numbers, how we can do that? Its value is 1, 1, 1 and so on. So here is the arrow that indicates yes, this value is 1 from 0 onwards, and before this value is 0. That's what the meaning of unit step sequence. Okay. Next, unit ramp sequence. Unit ramp sequence. Represented with R of n. R of n is equal to n or 0. N for n greater than or equal to 0 and 0 for n less than 0. Now, how we can represent this graphically? N. If n is equal to 0, its value is 0. If n is equal to 1, its value is 1. Because n, this is the same. Next, n is equal to 2, its value is 2. N is equal to 3, its value is 3. Like that, it will go. And so on. So it is something like a ramp. Not something like, it is exactly ramp signal, but discrete time signal. So this is what the graphical representation of R of n. And R of n can also be shown like this. 0, 1, 2, 3 and so on. Here is the arrow. And sometimes this can be said like this also. R of n is equal to n u of n. We have seen there t u of t. It is similar to that n u of n. Okay. Please make a note. I hope you have completed this part. I am erasing it. Okay. In the continuous time case, we have seen the relation between impulse, step and the ramp. Okay. So we have to see the similar kind of relationship in the discrete time case also. But to understand the relationship between them, first we have to understand something else, which is nothing but analogy between a continuous time case and a discrete time case. What is the similarities we are having? So let's analogy between continuous time and discrete time. Continuous time and discrete time. So let's say this is a continuous time. Let's say this is discrete time. First, usually the notation is x of t here, x of n here, x of t here, x of n here. Suppose I want to show a delay. Then here we can show it like x of t minus t naught. Here we can show it like x of n minus n naught. This is the usual notation of delay. Next, suppose if you want a dummy variable, then in the continuous time case we will go with the tau, and in the discrete time case we will go with k. Next, here integration. In the continuous time case, which is shown like minus infinity to infinity, minus infinity to t, x of tau d tau. So I am doing the integration with respect to tau, and the tau value is changing from minus infinity to t. So similar to this one, here we have to go with the summation. Summation means summation k is equal to minus infinity to n x of k, like that. So here tau value is changing, that is a dummy variable. Here k is the dummy variable which is changing from minus infinity to n. Next, one very important thing, differentiation. This is a dx of t by dt. Then what is the similar thing we have to go in this discrete time case? Okay. So many people think that differentiation. No, it is not a differentiation here. We cannot do the differentiation in the discrete time case. For only continuous time cases only we can do the differentiations. For a discrete time case we cannot do the differentiation. Then what we have to do? First, try to understand the definition of differentiation so that you can understand what is the similarity we can see in the discrete time case. First, let's see. You might remember dx of t by dt. From the definition of differentiation, it can be represented as x of t minus x of t minus delta t by delta t, where delta t tending to 0. That's what the differentiation means. Okay. In the similar manner, for the discrete time case, we will go with the difference. Okay. So delta x of n, usually represented with delta x of n. But here delta t must be as small as possible, that is tending to 0. But we don't have that kind of a facility in the discrete time case, because if I take x of n, next sample only we can take x of n minus 1. That's the only thing we are having. There is nothing like a delta n here which is very, very small. There is no such thing. So we always take the integers only. So what is the difference between them? 1. So this is nothing but x of n minus x of n minus 1. So this is the difference equation. So differentiation is similar to difference equation. That is delta x of n is equal to x of n minus x of n minus 1. X of n minus 1. So this is okay. Now let's see the relationship between delta n, u of n and r of n. If you observe carefully, summation k is equal to minus infinity to n minus infinity to n delta k. Let's see. If I take n value minus 1, so if I take the summation from minus infinity to minus 1, impulse function, so it does not exist, so its value is going to be 0. So this can be a 0 or this can be 1 depending on the n value. N less than 0, its value is 0. N greater than or equal to 0, its value is 1. So finally this is going to be u of n. This is going to be u of n. Okay. Now let's see. Otherwise, if you want to check it, let's say, if you want to find out u of let's say 2, u of 2, then summation has to be done. K is equal to minus infinity to 2 delta k. So this is equal to, and so on, delta minus 1, delta 0, delta 1, delta 2. Every value is 0 except delta 0. That's why it's going to be 1. So similar to that, you can verify for other values also. But I'm just stopping here. Next, if I take difference equation of u of n, that means u of n minus u of n minus 1. What will happen? Let's see. First, we have to subtract u of n minus 1 from u of n. First, let's see u of n. How it look like? Its value is 1 from 0 onwards. 1, 1, 1. So this is what u of n. I have to subtract u of n minus 1. If I subtract u of n minus 1, first we have to understand what do you mean by u of n minus 1. It is starting from not 0, it is starting from 1. So at 0, its value is 0. At 1, its value is again 1. At 2, again its value is 1. And so on it will go. If I subtract this u of n minus 1 from u of n, what is the result we are going to get? If I do the subtraction, then the result is 1 minus 0, 1, 1 minus 1, 1 minus 1, 1 minus 1, everywhere it's 0. So finally, we are left with, at 0, its value is 1, which is nothing but delta n. So difference equation of u of n is nothing but delta n. Okay, please make the notes. So these are the relations exactly similar to that of u of t delta t relations. Okay, but there it is integration, here it is summation, there it is differentiation, here it is difference equation. Okay, I hope you understood. Let's see next the relation between u of n and r of n. Are they exactly same as a continuous time case, or they are deviating from that? Let's check it out. Let's say summation k is equal to minus infinity to n u of n is equal to r of n. Is it correct or wrong? Is it correct or wrong? This is absolutely wrong. This is absolutely wrong. Why, sir? Why it is wrong? Why it is wrong? Okay. Because, try to understand. We know r of n values. Let's say r of 0 has to be 0. R of 1 has to be 1. R of 2 has to be 2, like that. So let's check one thing, then you can understand. Let's take r of 1. So what we have to get? We have to get 1. R of 1 has to be 1. Whether I am getting r of 1 is equal to 1 or not. Let's see. Summation from this definition. K is equal to minus infinity to 1 u of n. So u of k, sorry, this is actually u of k. U of k. K value is changing from minus infinity to 1. Then what will happen? And so on. U of, let's say, minus 1. U of 0 plus u of 1. We know for negative values it is 0 plus u of 0 1, u of 1 1. So finally this is 2. So is r of 1 equal to 2? No, definitely not. This is a wrong answer. This is a wrong answer. Then what is the correct one, sir? It is simply summation k is equal to minus infinity to, not n here, n minus 1 u of k is equal to r of n. This is the correct one. Suppose check it out. Again I am going with r of 1 only. Then we have to say k is equal to minus infinity to 1, sorry, 0, because n minus 1 0 u of k. If I take k value minus infinity to u of minus 2, u of minus 1, u of 0. All the values are 0, 0 plus 0 plus 1. Finally, this is 1. So that is what we are expecting. Yes, this is correct. So from here onwards, it is not summation from minus infinity to n. It is minus infinity to n minus 1 u of k is going to be r of n. Okay. Next. Is the difference equation of r of n, that is r of n minus r of n minus 1, is it equal to u of n? Here also it is not correct. Here also it is not correct. Then which one is correct, sir? Then we have to take r of n plus 1 minus r of n, which is equal to u of n. This is the correct one. Why? You can understand. Let's first draw r of n plus 1. R of n plus 1 means it is starting from minus 1. At minus 1, 0. At 0, its value is 1. At 1, its value is 2. At 2, its value is 3, and so on like that. So this is r of n plus 1. Then what is r of n? R of n means at 0 its value is 0, at 1 its value is 1, At 2 its value is 2, like that. If I subtract them, let's see, 0 minus 0, 1 minus 0, 1, 2 minus 1, 1, 3 minus 2, 1. So everywhere its value is 1 from 0 onwards, which is nothing but u of n. So this is the correct one. If you subtract them, then you are going to get u of n. So take it. If you subtract it, then the resultant is u of n. At 0 its value is 1, at 1 its value is 1, at 2 is also 1, like that, and so on, which is nothing but u of n. Okay, please r of n minus 1, please make a change, r of n minus 1 there. So I am just giving you the summary here, so that continuous time case, discrete time case, you can understand well. Summary. Continuous time case, discrete time case. In the continuous time case, let's say, integral minus infinity to t delta tau d tau. Its value is equal to u of t. Differentiation of u of t is nothing but delta t. Differentiation of u of t is delta t. Similar to that, in the discrete time case, summation k is equal to minus infinity to n delta k is equal to u of n. Difference equation, that is u of n minus u of n minus 1, which is nothing but delta n. So this is what the relation between step and impulse functions. Whereas step and a ramp function, let's say, integral minus infinity to t u of tau d tau, which is r of t, whereas differentiation of r of t, which is u of t. But whereas in the discrete time case, it is small deviation. Summation k is equal to minus infinity to not n, it is n minus 1, u of k is equal to r of n, whereas r of n plus 1 minus r of n, which is nothing but u of n. So this is the small deviation from the continuous time case. So please be careful here. Okay, take a note. Next. So in the continuous time case, we have seen real exponential. Here also we will see real exponential sequence. Real exponential sequence. In the continuous time case, it is represented with e power at. We have seen that, and e power at we have seen in the continuous time case, e power at. It can be growing exponential depending on a value greater than 0. Growing exponential, we have seen that. If a value less than 0, then we have seen that it is a decaying exponential. This is what we have observed in the continuous time case. Whereas in the discrete time case, the notation of exponential signal is a power n. A power n. So here also, depending on the value of a, it can be growing exponential, it can be decaying exponential. So how we can distinguish? Mod a, that is modulus of this a value, has to be greater than 1. Modulus of a is less than 1. Then we can say it is a growing exponential and it is decaying exponential. And it is decaying exponential. Okay. So let's check it out, some examples so that we can understand. 2 power n u of n, that means we are taking only from 0 onwards. 2 power n, let's say n. At 0 its value is 1. At 0 its value is 1. At n is equal to 1 its value is 2. At n is equal to 2 its value is 4, and so on. So it is a growing exponential like this. It's a growing exponential. So I can understand. So you can understand this one. It is a growing exponential. So if you observe carefully, what is the a value here? 2, which is mod a greater than 1. Next, suppose if I take minus 2 whole power n u of n. If I ask what kind of this exponential is, that means is it a growing exponential or decaying exponential? Most people will say it is a decaying exponential. But answer is it is a growing exponential. Still, let's see. What is the a value here? Minus 2. Then what is the modulus of a here? That is nothing but 2 only, which is greater than 1. So still it is going to be a growing exponential. How it is going to be a growing exponential, sir? See here. N is equal to 0. Its value is 1 at 0. N is equal to 1. Its value is minus 2. N is equal to 2. Its value is 4. N is equal to 3. Its value is 8. So it is growing only, but alternate positive and negative signs. Alternate positive and negative signs. But still we can call this as a growing exponential. It is also a growing exponential. And here also growing exponential. Next. If I take 1 by 2 whole power n u of n. What is the a value here? 1 by 2. 1 by 2. If I take the modulus, again it is going to be 1 by 2. Then from the definition it has to be decaying exponential. Let's check it out whether it is a decaying exponential or not. At 0, what is the value? It is going to be 1. At 0, it's going to be 1. At 1, its value is 1 by 2. At 2, its value is 1 by 4. At 3, its value is 1 by 8. So isn't it decaying exponentially? Yes, it is decaying exponentially. So I can say this is a decaying exponential. Decaying exponential. Suppose if I take another example, minus 1 by 2 whole power n u of n. If I draw this curve, again it is a decaying exponential, only the change is alternate positive and negative signs. What do you mean by that? Suppose n is equal to 0, again its value is 1. At n is equal to 1, it is minus 1 by 2. At n is equal to 2, it is nothing but 1 by 4. At n is equal to 3, 1 by 8. So if you observe carefully, it is also decaying exponential, only the change is it is going to be alternate positive and negative signs. Still we can call it is a decaying exponential. Decaying exponential. So remember, in the continuous time case, it is usually represented with e power at. A is positive, growing exponential, a is negative, decaying exponential. Whereas In the discrete time case, it is represented with a power n, and depending on the a value, that is modulus a greater than 1 growing exponential, mod a less than 1 decaying exponential. Don't consider this minus signs like that. Okay, so consider the modulus of that. Then we can decide whether it is a growing exponential or decaying exponential. Okay, take this. So this is about the basic signals what we got. Okay. Next thing what we have to understand is operations on the signals. Okay, give a heading. Operations on the signals. Operations on the signals can be divided into two types. One is operations on the amplitude, operations on the time axis. Suppose if you take y-axis, which is called as amplitude axis, if I take x-axis, that is nothing but time axis. Suppose if you perform the operations on the amplitude, then we can call it as amplitude operations. Amplitude operations. Let's see some examples you can understand. If I have given a signal which is x of t, which is existing between, let's say, 1, 3, whose amplitude is 2. If from this signal, if I want to find out 5x of t, 5x of t, that means if the signal is multiplied with 5, then what is that supposed to mean? Its amplitude is changing. So here 1, 3, amplitude is 2 into 5, which is nothing but 10. So this operation is called as amplitude scaling. Amplitude scaling. So this is also amplitude operations. I am not doing anything on the time axis. I am changing only the amplitude here. So it is amplitude operation. Amplitude scaling. Some more examples like addition of two signals. Suppose if you take two signals, then how can you add them? Then we have to add at each and every instant what are the amplitudes we are having. So addition of signals, addition of signals. This is also amplitude operations. Multiplication of signals. Next, subtraction of signals. Next, let's say differentiation. Next, integration. Integration. So these operations, amplitude scaling, addition, multiplication, subtraction, differentiation, integration, these are called as amplitude operations. Next, there is another kind of operations which are nothing but time operations. In the time operations, we will see time shifting, Next, time scaling. Next, time reversal. Time reversal. So these are the operations we have to discuss. So we won't see much of the amplitude operations because we already know how to add the signals, how to amplitude scaling. These signals, these are the things what we already know. So I don't concentrate much on the amplitude operations, but I will concentrate much on the time operations like time shifting, time scaling, time reversal. These are the operations we have to see in rigorous manner. Okay, just take this one. Time shifting operation. Time shifting. Okay, let's say if you know a signal which is x of t, if you know a signal x of t, from that we have to find another signal which is x of t minus t naught. Then if you could find x of t minus t naught from x of t, then the signal x of t minus t naught is called as time shifted version of x of t. It is a time shifted version of x of t. Okay. So if I ask simply, x of t is a one function of t, x of t minus t naught is another function of t. From this function to this function, functionally, what are the changes we have included? What are the changes we made? So we simply say t has to be replaced with t minus t naught. Functionally, I can say functionally t is replaced with t minus t naught. T minus t naught. T has to be replaced with t minus t naught. That is what the functionally we are changing. Functionally, what are the changes we are making? Okay. Next, let's see graphically what is happening. So for that, let's take one example so that you can understand clearly. Let's take a signal which is existing between 1 and 3 whose amplitude is 1. Let's call x of t. So this is the graphical representation of x of t. Can you represent the signal mathematically? X of t, can I call it is 1 when t lies between 1 and 3? T lies between 1 and 3. So this is the representation of x of t mathematically. Okay, t lies between 1 and 3, its value is equal to 1. That's what the meaning of it. So from this, we have to find another signal x of, let's say, t minus 2. X of t minus 2. So listen carefully. X of t value is equal to 1 when t lies between 1 and 3. If I change the argument, that means inside the bracket value, let's say m, small m. Suppose x of m is equal to 1 when the argument lies between 1 and 3. That means m value lies between 1 and 3. Here also exactly the same thing. So its value is going to be 1 when the argument lies between, that means t minus 2 lies between 1 and 3. T value lies, t minus 2 lies between 1 and 3. So these are the limits of t minus 2, but I want the limits of t. Then what I have to do? Add 2 for each and every term. Then what will happen? This is going to be 3, this is going to be t, this is going to be 5. That's what it is. Now if I draw this signal, how it look like? It is existing between 3 and 5. It is existing between 3 and 5. Whose amplitude is 1. That's what the meaning of it. Next, if I draw x of t plus 2, its value is equal to 1 when 1 less than t plus 2 less than let's say 3. Then t limits are -1, less than t, less than 1. So if I draw the signal, how it look like? -1, 1. This is what? X of t plus 2. This is what? X of t minus 2. So listen here. X of t minus 2, x of t plus 2. What exactly is happening here? From x of t to x of t minus 2, functionally, what are the changes we have done? T is replaced with t minus 2. That is what the functionally changes. Graphically, what is happening here? The waveform is shifted rightwards. The waveform is shifted rightwards by 2 units. That means 1 goes to 3, 3 goes to 5. This is shifted in the rightwards by 2 units. That means the right hand shift, right side shift. Or we can say in another way, here x of t is starting at 1 second. The signal is starting at 1 second. Whereas x of t minus 2 is starting at 3 seconds. That means the signal has to start at 1 second. Instead of that, it is starting at 3 seconds. 1 second, 3 seconds. Then can I simply say this is nothing but delayed by 2 seconds? So I can say this is delayed signal. So delayed signal is always moves in the rightward direction. Okay. Next, coming to this one. Here x of t plus 2, that means t is replaced with t plus 2. The signal is shifted leftwards by 2 units. That means 1 goes to 2 units leftwards means -1, 3 goes to 1 finally. So this is what it is happening. Can I say this is nothing but advanced version? Why? Because the signal has to start at 1. Instead of that, it is starting at -1. So it has to start at 1, but instead of that, early, that is nothing but -1 is earlier than the 1. So it is starting way before than the x of t. So I can say the signal got advanced. Okay, take it. The signal got advanced.